Okay, so we just got done talking about what the first derivative does for us. What does it say about the original graph? It tells us the increasing, decreasing intervals. Not only that, it gives us a way to find whether our critical numbers are minimums or are they maximums, or they're just horizontal tangents there. It's not necessarily minimum or maximum. But now, what does the second derivative tell us about the function? Okay, so it says if the graph of f lies above all of its tangents on an open interval I, then it is called concave upward on I. Let's draw a picture of what that may look like. So there's some function, and now I'm going to specify my interval I to go from right there to right there. There's I. Okay, so now on this interval, let's go ahead and find all of its tangents. So let me do that in a different color. Let me do that in blue. So we've got a tangent there, a tangent there, tangent there, tangent there. As you can see, all the tangent lines are below the graph, or if we read it one more time, it says, if the graph of f lies above all of its tangents, here's the graph of f, it's above all of its tangents, then we say that on this interval, the graph is concave up. As you see, it's going up, okay? Looks like an upwards parabola in this case. Over here, looks like a downwards parabola, just near it, near the maximum here. So we're going to say this is concave down. As you can see, if I choose any interval near here, right? And if we were to draw the tangents here, now let's go ahead and read the next part of it. It says, if the graph of f lies below all of its tangents, here's my graph of f in the black, and now here's the tangents around this blue interval I, and the graph of f is below all of its tangents, then it is called concave downward on I. As you see, it's going downward on this interval. Okay? So those are just two definitions. Okay, now we have, just like with the first derivative, we have an increasing, decreasing test. We also have a concavity test. Okay? Now it says if f double prime of x, so the second derivative, is greater than 0 for all x in I, then the graph of f is concave upward on I. So all that's saying is if the second derivative is greater than 0 on some interval, then it looks like that. It's concave up. A way I remember it, when it's greater than 0, that means it's positive. Concave up, you're opening up in the positive y direction. That's how I remember it, because the other way is if f double prime is less than 0 on some interval, then it looks like that, concave down. So again, how I remember this, if the second derivative is less than 0, it's negative, concave down, it's opening downwards. Okay? So this gives us a way to find where the intervals where a point is concave or a interval is concave up, the function is concave up or concave down. It's much like the increasing decreasing test where we take a derivative, in this case the second derivative, set it greater than 0, or take the second derivative and set it less than 0. So now we have another definition. It's a point P on a curve is called an inflection point if f is continuous and the curve changes from concave up to concave down or concave down to concave up at P. Okay? So, let's go ahead and look at a sine graph. That's a very good graph to look at for to see where the inflection point is. Okay, by looking at this graph, you can see from where it starts to about right there, this whole interval, we're concave down. And then from right here on this interval, all the way up until this endpoint, now keep going further, I'm only concerned with what I drew here, we're concave up. Concave down here, concave up here. This point right here is called the inflection point. It's called the inflection point right there. Okay? It's where the graph changes from being concave down to starting to be concave up. Or the other way around, it goes from being concave up to concave down. Okay, you can draw a similar picture to this. So now let's go to an example. Find the intervals of concavity and find the inflection points. Okay, so here's our function. F of x is equal to x cubed minus 3x squared minus 9x plus 4. We had this function earlier. So what we have to do is we need to find first the derivative, which is 3x squared minus 6x minus 9. Not only that, we need to find the second derivative. F prime of x is equal to 6x minus 6. Okay, now let's go ahead and find the inflection point. Now, find inflection point. Think about the first derivative test. And what did we have to do when we did the first derivative test? The first thing we had to do was find the critical numbers, okay? We had to take the derivative, we had to set it equal to 0. To find the inflection points, it's very much like finding the critical numbers when you do the first derivative test. It's very analogous to it, so that means we're going to take the second derivative and set it equal to 0, okay? So we just take the second derivative, set it equal to 0. This is a really easy equation to solve. So we have an inflection point at 1. Okay? So we just need the second derivative. We need the inflection point. So I'll write my second derivative over here. And inflection point x equals 1. Sometimes they ask you for the actual value, like the actual point of inflection. That's when you take the inflection point and you plug it into the original function, okay? And then it would be this x value and this y value, okay? If they ask you for the exact point of the inflection. This is where it occurs, this is what the point is. Okay, so now what we want to do is find the intervals of concave up and concave down. So concave down, that was the second derivative being less than 0. Concave up was the second derivative greater than 0. I hope you see the parallels in doing the first derivative test and this, the increasing decreasing test and this concavity test, okay? What we're going to do with this inflection point, we're going to put it on a number line, and now this number line is split up into two intervals. There's that blue interval. Here's the red interval. And guess what? We're gonna pick test values from each interval and see, we could just do concave up. So second derivative, here's 6x minus 6 is greater than 0. This one's easy enough. We could plug in our test values. Test value, so we're at 1, I could use 0. Test value over here, I'm going to use 2. Okay, so since it's greater than 0, we're looking for concave up intervals. We want to see where the derivative is positive. So plug in 0. Test value 0. 6 times 0 minus 6. Is that greater than 0? Well, that's 0. Is negative 6 greater than 0? Negative 6 is not greater than 0. So this interval did not work. So it's not concave up. If it's not concave up, it must be concave down. All right. Now, for the next interval, we do the exact same thing. We plug in 2. So test value, 2. 2 goes into there. You get 2 times 6 minus 6. Is that greater than 0? Well, 12 minus 6 is 6. Is 6 greater than 0? It is. So this interval worked, so this interval must be concave up. Alright, so let's go ahead and write our results. Concave up on the interval negative infinity to 1. Concave down on 1 to infinity. We have an inflection point at x equals 1.